Hi everybody, welcome to video number 28, Maximum Likelihood and Spectral Angle Classification in ENVI. So the last few videos we've been working on classifying an image from Yellowstone National Park, trying to break out areas of burned trees versus unburned trees, as well as water and rock. So in the last video I showed you how to do this using a decision tree classification in ENVI. In this video, I want to show you these two other techniques. So to start, I'll give you an overview of the maximum likelihood and spectral angle techniques, and then I'll show you how to implement them in ENVI. So to start out, we need to start thinking of spectral signatures not so much as a graph, but actually as a vector. And the reason we can think of them as a vector is because any combination of spectral reflectance values actually defines the coordinates of the tip of a vector in space. So it's easiest if we just think about this first in two-dimensional space. Imagine band 3 and band 4. And then imagine any pixel, for example, this urban pixel. It has a value for band 3, a value for band 4, and if we plot that in two-dimensional space, those two numbers represent coordinates of the tip of a vector. The vector would start at the origin and be a line going out to this coordinate. And that vector would be unique from all the other pixel vectors. So now if we add in a third band, so band 1, band 2, and band 3, we now have coordinates in a three-dimensional space, again of a vector tip, and the vector origin is again at 0 and it extends out to this point. So it's important to note that mathematically we can define vectors in as many dimensional space as we want, and typically the dimensionality of the vector would be defined by the number of bands you have. So if you have a 7-band Landsat image, you'd have a vector that's defined in 7-dimensional space. Of course, it's impossible to visualize that, but mathematically that exists. So our first algorithm technique that I'm going to show you for classification is called the spectral angle method. And we're going to illustrate this in 2D also. So imagine that we have 4 different pixels, A, B, C, and D. And we've plotted them up here with their band 1 and band 2 values. We can see that they are a little bit different from each other, and it doesn't necessarily look like any two of them are part of the same surface type. But we know that that could be a misconception. For example, what if one of these points was just a point in a shadow, such that its reflectance values were lower in both band 1 and lower in band 2? It might actually have the exact same reflectance values as B, but just be scaled down because it's in a shadow or on a topographic slope. So spectral angle classification allows us to deal with this by assessing which points or which pixels are on the same linear vector trajectory. So in this case, in two-dimensional space, we can define a single vector or line that actually goes through points A, C, and B, but does not go through D. Effectively, what this means is that pixels A, B, and C all have the same relative reflectances, just scaled up or down linearly. Another way to think about this is that all 3 of these points have the exact same ratio of band 2 over band 1. That ratio basically defines the slope of this line. So they have the same ratio because they're from the same surface type. They just have slightly different reflectance values. So here's the beauty of spectral angle classification. By paying attention to the vector that these fall on, instead of their absolute values, we were able to tell them apart from point D. Now, of course, point D also falls along its own vector, and that's going to look something like this. Okay? And the difference then between the surface type for A, C, and B and the surface type for D is quantified by what we call the spectral angle, or alpha. It's the angle in radians between the vectors that define these two surface types. So when we use this as a classification tool, you'll see in a minute, we're going to define a threshold for alpha and say if any two pixels have spectral angles that differ by more than some predefined value, predefined angle, then they're going to be in different classes. Okay, the second algorithm I want to show you is called the Gaussian maximum likelihood algorithm. So we've got the same distribution of pixel types I showed you before. These are urban pixels, these are water pixels, forest, hay, and corn. So we've got 6 different surface classes that we'd like to break out. Now, based on the clustering of these pixel values, we can assign a Gaussian probability distribution. That is, for any two coordinates, we can assign a probability that that particular coordinate set falls under the urban region. Okay? And in this case, this figure shows lines of equiprobability. So if you're on this line, you might have a 90% chance of being in urban. On this line, an 80% chance, 70% and 60% chance of being urban. And of course, your probability of being urban gets lower as you get further away from the center of this cluster. Okay? So first we define these Gaussian probability fields for each group or each surface type. Then you consider any pixel, for example this one, and ask for which group does it have the highest probability of being a part of. And of course for this one it has by far the highest probability of being in the urban group. Whereas over here this has the highest probability of being in the soil group. So just to visualize that in 3 dimensions, we can visualize these Gaussian probability peaks as being narrow or wide depending on the spread in the data. For example, that urban group is spread out, so there's no maximum high probability, but there's a low probability all around. The S, or sand group, actually was very tightly clustered data, so if you're in that cluster you have a very high probability of being sand. And so ultimately the way this technique is going to work, ENVI's going to go through, compute all the probabilities, and then for each pixel assign it to the class for which it has the highest probability. So let's go ahead now and have a look at how we can implement these things in ENVI. I've got the project up here. This is Yellowstone National Park, and I've got my 5 different classification end members. We've got burned, unburned forest, rock, water, and meadow. So why don't we first try the maximum likelihood classification, and that's going to be over here under the classification toolbar and maximum likelihood. I'll pick the Landsat image. Notice that I've already got my 5 regions of interest appearing, so you'll need to actually create regions of interest before you can do this. And I'm going to hold Shift and highlight all 5 regions of interest to let it know that I want to break the image into 5 different classes. My next step would be to define a probability threshold. Okay? It's assigning a probability, for example 5%, that the unknown pixel is within a class. So if the probability of being in a certain class is higher than 5%, then it will be assigned to that class. If it's lower than 5%, it will not be classified. So I'm going to go ahead and assign, let's say a 20% chance. So I'll use 0.2 in decimal form. And by the way, I can also assign multiple values. So I can assign a different probability value for each group if I want to. I think in this case I'll just stick with my single value 0.2, and I'll enter in a file name. Okay, so I've got my file name mlclass.tiff here, and then mlclassrule.tiff for my rule image. Okay, I'm going to hit OK and watch this thing classify. Okay, so our classified image has popped up now. Notice our water value in pink. We've got our bedrock in green. We've got burned areas in dark blue, unburned trees in light blue, meadows in yellow. So if you were to look closely at this, and you look at how it overlaps with the image, it actually does reasonably well. Although if you really get into it, you probably find some mistakes that need to be corrected. And you, of course, can go back and iteratively tweak your probability thresholds, etc. Also notice there was a few pixels of unclassified. Those are in black up here. Final thing to notice is a file was created called a rule file. If you look at that in Data Manager, you'll see it consists of 5 different rasters stacked into one TIFF file. And what this basically is, this is basically a raster showing the probability for every pixel of being a member of the given surface category. So this bedrock raster, each pixel in this file represents the probability that that pixel was part of the bedrock surface class. Okay? And so if we open up the rule files, for example, for water, which I've loaded up here, you can see that the areas over the water are very bright white. And if you get the cursor value out, we can see that those have really high values. So that's up here, showing that there was a high probability of those pixels being water. In contrast, some of these meadow pixels, extremely low probability that those pixels could have been water. And so we've got one of these rasters for all the surface types, so you can go in and assess for any misclassified pixels why those might have been misclassified relative to the cutoff probability that you specified. Okay, great. So for our next algorithm, I'd like to show you the spectral angle mapper. Again, that's over here in classification, and that'll be down under spectral angle mapper classification. So I'll open this up. We'll be classifying our Landsat image again. I'm going to import the end members from an ROI file. Notice you can also import them from a number of other files. I'll highlight my 5 ROIs that I've got open. And it loaded those. Notice I had to go look behind the screen because it opened this new window that was hidden back there. So now I'm going to select all of these end members. And so these are going to be the 5 things I'm going to classify into. I'll hit end. Now here's where I set the spectral angle parameters. Here, this is the maximum angle between any of the groups. So this is, if the angle is less than this, they'll be put into the same group or unclassified. If the angle is greater than this, it will be put into that group. As usual, I can have multiple values, so I could set a unique angular cutoff for each group. But in this case, I'll stay with a single value of 0.1. And once again, I've put in a file name of sa_class.tiff. That's for spectral angle class. And I'm going to put out another rule image. I've called that sa_class_rule.tiff. So I'm all set. My threshold 0.1 radians. I'll hit OK and watch this crunch. Okay, so the spectral angle classification image has popped up. Here it is. We got water in pink, we got rock in green, and so on. Notice that there's a lot more black pixels in this image. So based on that spectral angle threshold we assigned of 0.1 radians, a lot of pixels have not been classified into any group. A quick comparison with the maximum likelihood shows that that was able to capture a lot more pixels and classify them into groups. Now, of course, that does not imply the maximum likelihood image is better. Many of those pixels could actually be misclassified. It just means that based on the criteria we set, it was able to group more pixels into a class. So likewise, we've also got a rule image for the spectral angle output. In this case, the rule image is in units of spectral angle. For each pixel, what was the spectral angle between it and the mean spectral angle of the class it was supposed to be assigned to? So this image is the rule image for bedrock. Okay, here's a patch of bedrock. If I click on it, I'll see that the spectral angle is 0.02 between this pixel and the mean bedrock cluster. And that's good because this is inside that bedrock cluster. If I go over to water, the spectral angle is 0.58 between this pixel of water and the mean group for bedrock. And that makes sense. What this is showing us is that water is extremely spectrally different than bedrock, and there's a huge angle between their signatures. So that's it for classification in ENVI. Notice that all these images you've created as TIFF files will now be available for import into ArcMap or any other processing software. So please join us for the next video, number 29, where I'm going to show you how to open these images up in ArcMap and export them with a UTM grid. So ultimately we can go do some ground truthing of these images. Thanks for listening. Bye.